Hello and welcome to today's webinar. Wherever you're sitting in the world, thanks for tuning in today. Today we are joined here in our webinar by the people from Simerics, and we want to talk about how our software system from Friendship Systems CAESES can be combined with Simerics system for design and optimization. And specifically, we're focusing on pumps and valves today. So let's get started. On the side of Simerics, all the way across the Atlantic and the mainland of the US on the Pacific coast, I'm joined by Rich Moore, who is the Vice President of Strategy for Simerics. He's a member of the executive team, and noteworthy thing to know is that he was the 5th employee of the Space Claim Corporation. Additionally,
welcome to all the attendees today. Great to speak with you.
Hello, Rich. And additionally, we have Haiyang Gao, also from Simerics. He's a senior development and application engineer, and also a veteran in using and working on Simerics products. He's been with Simerics for 6.5 years, approximately. Yeah, finally, myself, I'm Matthias Brenner from Friendship Systems. I'm currently the head of sales for Europe at Friendship Systems. And before that position, I've worked in pre-sales and engineering here in the company. So I have done a lot of work with our software and on the applications that we work on. I've been with Friendship Systems for 10 years now. And originally, I'm a naval architect, so something slightly different than the applications that we're talking about today. All right, what do we have on the agenda for today? First of all, we will start off by having a small introduction about Friendship Systems and our software product CAESES for the people that don't know about it. And the same is true for Simerics. They will introduce themselves and their product. And then we want to talk specifically about a certain application case. So we will present that case. First of all, we will tell you how we build up a geometry model for this valve. That's what we want to talk about, and how that model is suitable for an automated variation. We will show you the simulation and the optimization setup, and then the results that we have obtained in that process. And finally, wrap up everything. So, as I mentioned, first of all, about Friendship Systems. So who are we? The company Friendship Systems partners up with our customers to solve any problems that they might encounter in their so-called simulation-driven design process. Basically, that's all kinds of processes that where you want to optimize something based on simulation. We have more than 15 years of experience now in the fields of geometry parametrization and optimization. Initially, in these 15 years, we started in the maritime industry. And then over the years, we also moved in a lot of other applications that are concerned with flow optimization in general. The company is located in Potsdam in Germany. This is unfortunately not our office that you see here in the picture, but one of the beautiful palaces in the city of Potsdam that you're welcome to come see and visit here. And we mainly produce a software product, which is the CAE platform CAESES. So let's talk about what we do. And I mentioned our main business is this product CAESES. And this product comprises mainly two parts. The first one is an optimization part. This provides all the tools that are necessary to run an optimization process. So the algorithms that you might need for optimization or for a design of experiments. Then you generate a lot of data in the optimization. So those data, geometry data, simulation data need to be managed. So that's also part of that. And then finally, we want to draw some conclusions from that data, and therefore we need some assessment tools. The second part of CAESES, and this is probably the most important part, or the part that distinguishes CAESES the most from other optimization systems, is a very specialized CAD tool. It's specialized insofar that we focus on providing geometry that is directly ready for simulation. Also, we want to be able to do geometry variation in a very robust and easy way, also for very complex geometries. And finally, provide an efficient parametrization so that you can have a flexible model, but not too many parameters, which will save time during the optimization. And to complete the whole process, we need a tool to provide the performance feedback on the geometry that we're analyzing. And this is done by connecting to a CFD solver. It's important that we have a very robust meshing process for the different geometries that we're creating. It needs to run in batch mode. And this is done very nicely by Simerics-MP, as we will see later on. So the first question that we can ask is, why should I automate my design process? So there is a lot of factors, laws, regulation, competition, and so on that demand a very high level of performance in the products that engineers are designing. And old processes, which means you're doing manual iterations from CAD to meshing, CFD, post-processing, and then back to CAD, are obviously very time consuming. This increases the development costs of the products, and it can certainly lead to an improved design, but not necessarily to an optimized result. So there might be the situation that the targets of the design are not met. And in that context, automation can, of course, shorten the development times, reduce design cycles, lead to optimized designs. This is directly addressing the points above. But also an important point, I think, is that you can very quickly get a large amount of knowledge about the product's behavior by seeing what are really the drivers of the performance in terms of geometry parameters and things like that. So it really helps to gain a lot of information in the early design phases. And our tool CAESES is meant to give you control over this whole automated process in one integrated user interface. The second question, I mentioned the very important part of CAESES is our specialized CAD kernel or CAD part in CAESES. So why would you need another CAD system? Many of you probably have a CAD system in-house. So from our experience, the most bottlenecks that people encounter when they are setting up or running an optimization or design exploration process are in fact related to the handling of the geometry. So often the geometry variation with the traditional CAD system does not work quite smoothly or robustly. So you change parameters and the model might break down, that cannot be regenerated. Another factor is constraints. So we might have manufacturing, packaging constraints, things like that, that are difficult to consider or even fulfill automatically. Another factor is the work division. So simulation engineers often are not the CAD operators themselves, but they depend on a CAD department to provide different variants of the geometry if they want to change something. And that, of course, is not very fast and also not very suitable for automation. And finally, a point that the CAD model that comes out of the CAD system might not be suitable for simulation. So it's not watertight, the level of detail is maybe too high for the types of simulation that you want to do, and so on. So these are basically the points that we're trying to address with our specialized CAD system. So how can you make use of CAESES? Typical applications for CAESES are in the maritime field, ship hulls, propellers, appendages, but also powertrain components, so everything that you encounter inside or around an engine, turbomachinery, is also popular, gas turbines, turbochargers, and so on, and also part of turbo machinery, at least in part, are pumps, which is a very good application for CAESES. So we can work, of course, on all different kinds of pumps. You see here in the picture gear pumps, but also dynamic pumps, and we can work on impeller geometries, blade geometries in very much detail and optimize them, but also the different inlet outlet geometries or volute casings, as we see here in the picture. Everything is can be worked on in a lot of detail and used in the optimization process. And another application that we want to talk about today are valves. One of the examples here is the case study that we want to look at today, which is a spool valve, but also all kinds of other control valves and so on. So this as a short introduction about Friendship Systems and CAESES, and now I want to give over to Rich, who will give you an introduction into Simerics and the capabilities of their product. Let me switch over. Please, Rich, the floor is yours.
Thank you, Mattia, and just confirm that you can see my slide for me, please.
I can.
Okay, good. Thank you so much. So, Haiyang Gao and myself, Rich Moore, we are talking to you today from world headquarters in Bellevue, Washington. We also have an office south of Stuttgart, and also an office in Detroit, and an office in Bangalore, India. We are the developers of the award-winning Simerics-MP CFD software platform. Simerics-MP is both a platform and a product that we have sold to analysts around the world for 11 years. And also built on top of Simerics-MP is the PumpLinks product that is used for pumps and valves and compressors, Orca 3D Marine CFD, which is sold by Orca 3D for marine design, Simerics CFD for SolidWorks, which is sold by SolidWorks resellers, where we have embedded Simerics-MP into the SolidWorks platform, and then Creo CFD, which is we've embedded Simerics-MP into Creo, and that product is sold by PTC on a global basis. And then for today, of course, CAESES Simerics-MP solution, where we have integrated the high-end CFD physics that we've developed and sold for 11 years with CAESES. And we're really excited about what that means for you and what that means in the overall CFD marketplace. If you look at this slide, there are 5 million engineers in the world, approximately 100,000 analysts on the right-hand side that use CFD. But you know what? Most analysts don't know how to use the parametric CAD systems, because those parametric CAD systems were designed for engineers and designers. CAESES, Friendship Systems, designed a CAD system for the analyst on the right-hand side and for the high-end engineer a little bit to the left. So that is very interesting. So I'm going to speak to you about two significant market voids in this marketplace. You see here the void. The industry analysts, by the way, predict that there are 4 times more users in this market space than the 100,000 high-end analysts using CFD on the right, and the few thousand CAD users using low-end CFD on the left. So Simerics and our CAD partners plan to fill this void by embedding and integrating our technology with the companies that drive and create geometry. So the last 10 years, we really have been focused on the analyst marketplace with a new CFD software architecture called Simerics-MP, and it has many advantages, templates, an automatic and efficient mesher, that meshes 100% of the time, regardless if you have clean or dirty geometry, less iterations on the solver, and superior physics in terms of accuracy and speed. Lots of analyst customers, a productive international reseller group, and we will just continue to add more and more functionality for the analysts so that we can create our core. But then our next 10 years now is focused on this void. Orca 3D, Simerics-MP for SolidWorks, Creo CFD, and the CAESES Simerics integration. If you look at this market map and you say, where does the CAESES Simerics product fit on the map? It goes right here, and it goes so well, because if you're an analyst today on the webinar, you're probably not personally using CAD, or if you're a high-end engineer. And now you can take advantage of parametric CAD in a way that you can connect all the parameters to the Simerics-MP platform. So I think just some advantages that you can look for in the case that we're going to start in just a couple minutes is you can now associate the fluids based on the parameters and the optimization that you've come up with. Of course, to make that happen, it has to be fast, and it creates a secondary workflow that we're very excited about called Analyst Parametric CAD to CFD to optimization. And when we speak to friendship systems, we like to say this is priceless.
Okay.
Let me turn it back over to Mattia.
Yeah, thank you very much, Rich. So back to myself. Now I want to start talking about the specific case that we want to present today. There is just one thing that I forgot to say in the opening. Sorry for that. If you have any questions that might come up during the webinar about the things that we're showing or about some other things that you have in mind, please feel free to post the questions in the GoToMeeting panel. We will take your questions. If we have some time at the end before 1 hour has passed, we might answer some questions live. If there is no time left, then we will get back to you by email or in any other way. So don't hesitate to post your questions. So now let's get started with the example case. What we want to look at today is an optimization that we ran for a spool valve from the company Diplomatic Motion Solutions in Italy. And specifically, this is a so-called pilot operated distributor valve, and it's controlled by either a solenoid, so either electrically or with a hydraulic control. You can see some pictures here on the right. So it's, as you can see in this overview picture at the top, it's one of the larger valves in the product portfolio. And yeah, you can see also some cut views in the bottom that give you an idea of what we're working with here. The maximum pressure for this valve is 350 bar, and the maximum flow rate is 1,100 liters per minute. So what we want to optimize here is the mass flow rate. So we want to get a higher mass flow rate in a certain configuration of the valve that I will show later on. And we want to do that by modifying the internal channels of the valve. So what you see here in the cut view, and what you will also see in the next pictures that are coming. So first of all, I want to talk about our approach for the geometry parametrization for this case. So we have two different approaches for geometry variation in cases, and we used both of them on this case. And the first one is what we sometimes call partially parametric approach, or maybe commonly known as morphing or deformation. So it means we import a certain geometry and then we can apply some deformations to it. And this is what we did here for the so-called T-port bridge connection. So here at the bottom, the cylinder is the T-port of the valve. I think we can see it here in the picture, denoted by the letter T. And then we have this bridge connection that connects both sides of the valve. And we applied a so-called morphing box to this geometry. And here we have different parameters: the expansion in the middle of this bridge, the vertical translation in the middle of the bridge, expansion on the two sides, and also a vertical translation on the two sides. So this is just a deformation applied to the imported geometry, no rebuilding or no parametric model that has been built there. And for the other ports of the valve, the so-called A, B, and P ports, we have used our other approach that we can make use of in CAESES, the so-called fully parametric modeling, where we basically build a parametric geometry model from scratch for that part of the geometry. And here we also have several parameters to control it. The first one is the box height. So we have here this blue boxy shape in the channel, which we can change in height. We can also rotate it around in horizontal axis, as you can see in the animation now. We can shift that box geometry to the side, and we can change the height of this cap, which is on top of the box. We can also rotate that cap. We can change the cylinder height. So this is the cylinder where we have the connections then of our hydraulic system, and the cone angle on top of that cylinder. Then the outer radius of this ring. And finally, this what we called here bottom fillet. This is here the this lower connection between the ring and the cylinder. Yeah, and these are basically all the parameters that can be used to control this geometry and to vary the geometry. And of course, the next step, once we have our geometry parametrization or the variation set up for our geometry, the next step is the export, so that we can use the geometry in our flow solver. And in this, we can export it in many different formats and configurations. And in this case, we exported to Simerics-MP in the so-called STL extract colors format, which means here that each geometry patch that we want to be able to distinguish gets a different color. You can see in the picture on the right a little bit the different, so the inlet and the outlet and other parts of the geometry have slightly different colors. And when we export in this special STL format, each color is exported into a separate STL file. And when we import these STL files into Simerics-MP, then the different boundary patches of the geometry can be identified by their names. And this associativity through the names of the different boundary patches allows for an automated mesh regeneration when we're running our optimization later on. We will see a bit more details about this then later on. And then the next step is to connect CAESES to our solver, which is done through our so-called software connector, which is the generic interface. And this interface has 4 quadrants. The first one is for the geometry export. So here we drag and drop the geometry that we want to export. And as you can see in the dialog here on the left, we can select the type of export, so the format, and also the file name and things like that. In the second quadrant, we find any additional input files that our external solver needs. So additionally to the geometry file, here we have the SPRO file for Simerics, and we have a shell script that launches the Simerics executable. Let's take a bit more closer look at the SPRO file. This is the Simerics-MP project file, which is basically the main connection between the two programs, between CAESES and Simerics-MP. And this SPRO file is mostly created automatically by Simerics-MP. There is just a little bit of edit that has been done. Haiyang will show that later on in his part in detail. And when we have this project file loaded into CAESES, we can parameterize any value that we encounter in that file in CAESES, so that we can also change certain settings from within CAESES. Let's say the mesh settings or the boundary condition at the inlet or outlet and so on. Then if we go to the lower part of our software connector, we find the result files. Here we can specify whatever we want to load as a result into CAESES after the computation has finished. In the third quadrant, we have we can load screenshots, flow fields, other type of data. As in this example, the NSide file that is generated by Simerics-MP that we could use to do some post-processing within CAESES. And in the last quadrant, we have specifically also some result files that we're loading, but here we're specifying certain values that we're reading from these result files, which can be seen here in this next picture. So this is, for example, the integrals text file, which is basically time history of integral or integrated values that comes out of Simerics-MP. And here we can specify which value we want to read from that file for our optimization process as an objective, for example, for the optimization. So much for the geometry setup and the connection to Simerics. And now I would like to give over to Haiyang to show the CFD setup. And he will also do a short live demo for the setup of the case.
Okay, hello everybody. Moment here. Share the wrong windows, sorry. Sorry about that. So here I'm gonna go over a few slides here, and then I'm gonna do a live demo. So what the user for this CAESES Simerics setup will do is first they need to set up a baseline case, and then use this baseline case to get that S profile that can be used in the CAESES software. So here in the lab, I show the first 4 steps. It's basically typical for any Simerics setup. We do the geometry import and mesh and the interfaces, model setup, and the volume boundary conditions. After this, you can just run the simulation and test it out, and just like any normal CFD simulations. The last step is we need to project the S profile for the cases. So very straightforward is the geometry import. We just import all the STL files this case is generated, and we'll see this geometry import here. Next step is the meshing. We use a binary tree based mesh. It's basically automatic measure, but the user still got a lot of control. It has low cell count because we use a cube typed mesh in the middle of the domain, and in the boundary we cut the cell to fit a specific feature, geometric features. It has a really easy local refinement settings, high accuracy, and really fast convergence. And I think most important is automatic. You just click a button, input a few parameters, and you're done. Because we sometimes generate separate volumes, we need to connect them together via sliding and moving interface. We have this mismatch grid interface, which basically connects multiple volumes together. It's automatic, dynamic, and implicit. basically the user doesn't need to worry about much, and just needs to select the surface and click a button. There are some setup for the model and volume boundary conditions. I won't go into any details here since I'm gonna do a lab demo later. After we set up all the conditions and run the model correctly, we basically need to do some operations. So extract the file we can import into cases, which we can do a parametric study. So I'll do some demo later, but this is basically the steps if you don't like to take notes. Okay, let's go to the path links window. Let's start by adding a new project. Import the geometries from cases. Here you see the geometry. We have 3 volumes: the A port, which is the serve as outlet for this simulation; P port, serve as inlet, and the spools. Let's save this file as wow. Make sure that scale is correct because cases use millimeters in this file, and we use meters, so we need to scale it down to millimeters. And then we start with the meshing process. We select general measure here, and we select general measure here. We have some control for the mesh size. This uses relative size, so it basically doesn't need to change the number much for larger and smaller models. Here I just refine the mesh a little bit for this case. Let's select all the surface for the A port and click Quick Mesh. So you see the mesh already automatically created. Here you can see the mesh. Basically, it's a more square cubic shape in the inside, and some cut cell on the boundary to fit all the small geometric features. Let's do the same for the other 2 volumes. To some third volume. So we got all 3 volumes generated. The next step is connect them together with the MGI interface. All we need to do is select all the connections. MGI, and click this button. One here. Select the correct boundary for the meshing. I think I didn't load the correct file, sorry. Okay. Sorry about that. I'll repeat a few steps. Okay, let's connect the MGI surface. Just pick up. Okay, this time it's all connected. Okay, then let's go to the model setup. We select a few physical models. Flow turbulence here, and we need to add a streamline for some post-processing. And then we set up some volume conditions. So we select all the volume. And for this case, it's some kind of oil. So we change the density and the viscosity settings. And for the boundary condition, we have an inlet, which we set as total pressure inlet. Set the inlet at 50 bars. And we go to the outlet using a static pressure outlet. Let's go to 45 bars. Sorry, just bar. And then we can test out the simulation. Oh, one moment. Inlet, we just need to turn on the streamline to release some streamlines. So you can see a pretty good convergence here. It shows some coloring by velocity magnitude. So some pressure plus. So this is basically the setup of a Simerics model. For normal users, you basically just stop here. But for now, we basically need to extract the S profile for the cases we can partner with. So for this, basically, we need to, each time we load this file, we want to import some new geometry, basically new CAD surfaces from the generated by cases. And also we use this new CAD surface to generate new volumes. So the first step is we need to delete all the old volumes. We click all the volumes and click the delete button. Here we have a notice, basically whether we want to delete the volume or also both the volume and conditions. Here we want to keep the condition because all the conditions are what is associated with the volume names and which set up the simulation. So we click no. So we can see all the volumes are disappeared, but all the boundary conditions, volume conditions, and the MGI interface are still there as an empty shape. The next step is we need to delete the geometry because we want to import new geometry for each new simulation. So we delete all the CAD surface here. The third step is we need to set up this build mesh to say it auto build when the project opens. Basically, each time we load the file, we build this mesh from a new set of CAD surface geometry automatically. We set all three volumes to yes. And we save this file as something else. Yes. Wow. What's this? Okay, let me close this window, and we can go to this file and open it with text editor. So this is the file Mattia was talking about, which is the connection between cases and the Simerics. Here we have all the conditions and all the volumes here, but the only thing we need is the import of the new geometry. So let's copy a few lines here. Import some new geometry here. And the import block is fairly simple. Basically, we import this file with this scale as this name. The name is the most important thing, since what would we do with associate to associate what surface geometry with actual simulation properties. So the name has to be consistent with the thing you declare here and the name you set boundary condition and the mesh there. So basically, you can save this file, and we can open this file. Basically, once we open this file, it automatically builds a new mesh, and generate the new simulation, which you can run directly. And this file is what the cases takes. And each time the cases load this file in their shell script, it will generate the new mesh based on new geometry and set all the conditions. You can see all the conditions we just set is still there. And all the volume conditions we just set is still there. All the surfaces that we connect is still there. So we can just run this one directly with a new geometry. That's what the cases does. Okay, that's the part of my demo. And the next, we'll hand it back to Mattia.
Okay, thank you very much, Haiyang. So now we have seen the CFD setup and how the two programs work together. So what I want to show you next is the optimization setup. So for the optimization that we ran in this case, we focused on a specific configuration of the spool valve, the so-called PA configuration. So it means the P port is the inlet and the A port is the outlet. I showed it here in the picture. It's basically two of these ports that are connected. Basically, you saw the geometry for the CFD also in Haiyang's demo. And the other two ports of the valve are closed. So what we did beforehand, we had the CAD model, which has the spool in it, and we extracted the flow volume. So you can see the spool here in the middle between the two ports. Then we take all what's in between the ports. And here in red, we have our flow volume. And this is basically the geometry that we're running in the optimization and in the CFD, as you saw in the Simerics demo right now. So then we set up the optimization. And here you see basically the CAESES user interface and what you need to set up. In the first step, we ran a DOE, and this is the interface, which is also similar when you run an optimization. So here we set the number of variants that we want to generate. Then we have a list with all the design variables that are going to participate in our design of experiments. And for each design variable, we set a lower and an upper bound. Then we have all the results that we want to evaluate for each design variant that we generate. In this case, we just have the flow rate, which comes back into CAESES as a result from Simerics. And finally, you can specify some constraints if needed. In this case, we just monitored the volume of the ports. And yeah, if you run an optimization or a DOE, you get a table like you see here on the left with all the results. And then you can, for example, sort your design variants by the objective function. Here they are ranked in ascending order, and then you can select the best design with the highest flow rate. In this case, don't be confused. The flow rate is set negative here, so the lowest value is the highest flow rate. So just in case this seems strange here. So the whole optimization process was divided in 3 steps. So in the first step, we ran a design of experiments with all geometry parameters of one of the 2 sides of this configuration. So in this case, we use the outlet or A side of the configuration, which is shown in the picture. And we used all of the 9 parameters to run the design of experiments. And the inlet side or P side is kept fixed. And this DOE ran 100 designs. And then after this first DOE, we reduced the parameters to the 4 most influential ones from the previous study. In this case, we had the box rotation, the box shift, the outer radius of the ring, and the bottom fillet were the most influential parameters on the result. And then we used these 4 parameters for the both sides of the configuration. So in total, we have 8 parameters, and we ran another 90 designs. So this was the second DOE. And then with the result from the second DOE, so the best design that we obtained in that step, we start from there. We started an optimization using the same parameters as before, so the four most influential on both sides, and we ran another 50 designs, and then we obtained our optimized design. So this is just let's say an exemplary optimization process. You can do run optimization, of course, in many different ways. You can use genetic algorithms, multi-objective algorithms, or as we did here, a combination of a DOE first, where we do a very broad scan of our design space, and then in a second step, we do a local optimization in the region where we had identified the best designs. Here you can see some of the results from the optimization, or actually from the DOE process, from the second DOE, where you can see the correlations between what is highlighted here, especially our objective and the different input variables. And we can see quite clearly here that there is 3 variables that have a more pronounced influence, which is the outer radius of the inlet and the bottom fillet of the inlet part, and the outer radius of the outlet, which are these diagrams here that have a stronger slope. Here we see what happens during the final step of the optimization run. So we start somewhere, and then as the optimization is progressing, we are getting closer and closer to a convergence and to an optimal design. So let's look at the final results. You can see already in the figures at the bottom that the mass flow rate through this configuration of the valve was improved by 8.65, so between 8.5% and 9%. And just to show you the difference between the geometries, which is not so easy to see, I can switch from one to the other. Yeah, you can. I think you can see it here. Especially here, this bottom fillet, the connection between the ring and the cylinder is changing very strongly, and we saw that that has a very strong influence. Okay, these are the geometries. I also have some comparison pictures for the CFD results. These are the streamlines for the baseline and for the optimized design. Again, let me go back and forth. Okay, I don't know if you can readily see something here, but these are the streamlines. And then finally, we have the velocity distribution, which I think here is a bit easier to see the difference. So we have some higher velocities here in the optimized design. So you can see a little bit the differences in the coloring. So let me summarize what we have done here. We have demonstrated a methodology for designing and optimizing flow-related geometries, and we use CAESES for the CAD and geometry variation, as well as for the process integration, and Simerics-MP for evaluating the performance of our designs. And we demonstrated this approach quite successfully on the optimization of a spool valve. But of course, the same methodology can be used in a multitude of different applications. So it doesn't have to be a valve like this. So it can be applied in very much the same way to pumps, marine applications, general turbomachinery applications, powertrain components, and so on and so forth. So the principle is always the same. And as you can see in this nice testimonial that we got from Diplomatic, the company that was involved here, the very big benefit that comes out of this automated process, as I mentioned at the very beginning, is really a speed up of the design process so that you can obtain these results in a very fast way. So this concludes the content of this webinar. So if you want to know what to do next, if you would like to get to know CAESES because you're not a CAESES user yet, then you can check out a special promotion that we have in connection with this webinar on bit.ly/pumpsvalves2018. This is a nice package, I think, that allows for a very easy evaluation of this product in one of your real life test cases. And since you followed this webinar today, you can use the promotional code that is shown here, PV2018, on that site to get the 20% reduction in price on that offer. So again, the link is bit.ly/pumpsvalves2018. And if you would like to try Simerics-MP, because you're not a Simerics-MP user and you found what was shown here interesting, the meshing approach, the fast solver, and so on, then you can contact Rich at rich.moore@simerics.com, and the phone number that is shown here, 978-376-1763. And yeah, Rich will certainly help you to get to know Simerics-MP a little bit better. So we have a few minutes left, so we can use the time for Q&A. I have two questions that came in here that we can answer together. Maybe Haiyang, Rich, if you're also available. The first question from Shayi was, why don't we use a step file for the example as the geometry export format, since it usually has more high fidelity surfaces that define the geometry compared to an STL file? So maybe I can start answering, and maybe you can add something to that, Haiyang or Rich, whoever wants. I mean, first of all, there is two important components in the geometry exchange that we're doing here for the process automation. One might certainly be the geometry fidelity, which is what you're asking about, Shayi. And the other factor is the ability to automate the process and to identify certain parts of the geometry by their name, which is very crucial here, as Haiyang has shown here. So that was a major, I think, factor here in choosing this special STL format, because it allows us to very easily to have that connection with the names. Of course, it's a discretized format, so the fidelity is a bit lower. It can be tuned in CAESES, so for each part of the geometry you can set the resolution and so on for your STL export. But I don't know if in this case step would be an option. Maybe Haiyang or so.
Yeah,
you can say.
Yeah, so Mattia, and for the attendee who asked this really good question. So what we demonstrated today was, of course, the transfer of STL. As part of Simerics-MP, the product platform, we have a new module called Fluids Volume Modeling. And in that Fluids Volume Modeling module, it has certain import and export capabilities. And one of them is, in fact, STEP. So you can use either STL, as we demonstrated today, or if you have the Simerics Fluids Volume Model number 1, Roman numeral 1, then you can use STEP. So either way is a terrific workflow.
Okay, I think that should answer it more or less. If more questions come up regarding that, then we can follow up by email. Then there is two questions which are quite similar, and I think I can answer them. From Christian, how are the DOEs generated, by hand or automated? And from Oliver, which kind of sampling method is used for the DOE? So in this case, we're first of all, they're not created by hand, the DOEs, but were created in an automated way using a DOE algorithm, and that algorithm uses a SOBOL sequence as a sampling method. So this is what we have used in this case. So the SOBOL sequence, you can look it up. It's a quasi-random, low discrepancy sequence that is supposed to cover a multidimensional design space in a as uniform as possible way. That's what we used here. There is also other sampling methods available in CAESES like Latin hypercube sampling and other possibilities. And finally, there is a last question, which is also related to the optimization method from Hamid Riza, which is what optimization algorithm do you use after the DOE and why did you choose that method? We used a so-called tangent search method, or T-search in CAESES, which is a single objective optimization method, which we have, in this case, we just need a single objective method. That's why one reason why we chose that, because we have only one objective, which is the flow rate. And we selected that method because we want to run only a local optimization in the vicinity of the best design from the DOE. And yeah, we have good experiences with that method, and it's one of the methods we suggest for this kind of application, local single objective optimization, because it's pretty robust and also efficient. I saw one more question that just came in. How do you set up the fully parametrized model in CAESES in a CAD-like environment, is the question from Christian. Yes, so basically CAESES is more or less a CAD tool. So a big part of CAESES is CAD modeling. So we have a lot of capabilities that you would also find in other CAD tools, but we also have some very, let's say, unique ways of defining things by the way we set up the models using relationships, dependencies between different parameters, objects, geometry parts, and so on. That makes it very robust in the variation. So our focus in the end is always to vary the geometry. That's the difference to other traditional CAD systems, that where you can build all kinds of geometries, but it's very difficult to vary them quickly and automatically. And that's our focus. So we have to put in some thoughts when we build up the model so that it is suitable for this automated variation. Okay, I think we don't have any further questions right now. Of course, if any other question comes up afterwards, then feel free to connect to us and talk to us about these questions. Thank you very much for joining this webinar. I would really appreciate, after the webinar, there is a very short questionnaire. It takes maybe just 1 minute to fill out. So I would appreciate if you fill out that questionnaire. And again, thanks for joining. We hope to see you next time in one of our next webinars, or to hear from you. Here are again contact information for Rich and myself, and have a good rest of the day. Bye-bye.